Okay, cool. So checking it out. Number one, pretty doable for everybody. Okay, as we're looking, this question, it's just a review of all that transformation stuff. As I look at this, first off, what degree is this function? It's a second degree, which means its graph is going to be what shape? It's a parabola, so it either has a minimum or a maximum, right, depending on what it does. Now, as we look at this, is this in general form or is this in vertex form? It's vertex for sure. And where is the vertex? At the point 2, 1. Now, as we think about it, if we go back to the parent function, it just starts at the origin. Right at the 0, 0 is where that bottom of that parabola would be. I've now moved it to get to 2, 1. I must have gone 2 to the right and 1 up. Like, that's what we've done so far. There's one more little piece that happens. And remember, if we're trying to pay attention to the order, we would do inside the parentheses first. So I move right 2. What does this negative out front do? Flips it over the x-axis, and then it moves up 1. So what I see for this answer, just as we're looking at it, if we go in order, and I wouldn't fault you since we haven't been talking about this as frequently as we did earlier in the year, but we should see that this thing goes right. How far? 2, and then reflect over what? Good. So I'm just going to say over, I'll just write it all out, x-axis. And then the last one, what does this plus 1 do? Up 1. All right, there it is. Okay, on Bravo, without having to graph it, whether you interpreted that, I hope you interpreted it as not graphing it at all, whether by hand or with calculator. Can you tell me if this is a smiling upward parabola or a sad down parabola? It's a sad down parabola, which means that vertex is a minimum or a maximum? It's a maximum. So these questions oftentimes show up over and over. The maximum is at which point? 2, 1. And I'm okay if we write it that way. We could say that the maximum is 1 at or when x equals 2, but this is equally as good. Cool. All right, that first one, thumbs up, thumbs down, just rough feeling for it. Okay, so checking these out, a little bit harder. Now, my hope is that even if they seem like ugly at first, as long as you're trying, you're probably going to stumble upon the right path. So let's just check it out. I'm going to call in some random people here, and let's see who we get. We're missing a bunch of people, so if I call somebody that's not here, don't hesitate to let me know. There's 26 total. All right, number 25. I don't know who that is. We'll try it. Briscovia, when you look at 2a, is there a first thought that comes to mind? Love it. I'm good with that. Okay, when I distribute here, what do I get, anybody? I do this first distribution. ABX. Can I just call it A? Like, it is A times 1 or 1A, but I'm just going to call it that. And when I distribute onto the right side, what would I come up with? BX plus AB. All right, if this was your first initial gut feeling, love it. This is exactly what we need. We're trying to solve it for what? And if we think all the way back to pre-algebra, algebra 1, what do I do when I have an equation? I want to do what with the x's? There's an I word I'm looking for. Let's isolate them. So I don't really care which side we move it to. It doesn't matter. Do you want all the x's on the left side of this equation or on the right side? So I heard both, and I think that it was strictly to make it both, but I'm okay with that. So let's do this. I'm going to subtract a bx from both sides, and then I'm going to get rid of this as well. I'm going to subtract a from each side in the same step. Now, there's some wonky stuff that happens because notice these aren't like terms. They can't combine yet, but we can just write it all out so that everything with an x is on the left and everything without it is on the right. When I do all of these subtractions and things, I'm left with what on the left side of this equation? ABX, I'll give you that one for free. What else is there? Minus BX. And that is equal to AB minus A. So all we've done now is distribute and rearrange. What is the whole point of having everything with an x over on the left side here? We have something in common, right? What's that F word that we get to use here? Factor. What can I factor out of these? So you could factor out an A, but remember, what am I trying to solve for? Can I factor an x out of this? Let's try it. If I factor just the x, even though there's a little bit more, what would be left behind, Zed? AB minus b. And that's still all equal to this lovely AB minus a. We are one step away from solving this. And I know it's ugly because we have a whole bunch of variables, but this is just x times whatever this number winds up being, right? If I have x times a number, how do I get it to be just 1x? Let's divide by whatever that number is. I'm going to divide, and it's ugly for here, but it's a literal equation. There's no numbers in it. That's fine. I'm going to divide both sides by what? AB minus b. When I divide both sides by this, these guys fall out, and it looks like we are left with our solution. X is exactly equal to AB minus a over AB minus b. It looks like stuff maybe will fall out, but if we try to factor these, nothing divides out. I would stop right here. I would not go a step further than this. I might actually write it nicer on one more line, but cool. I mean, we can factor it out, but let's just see what happens. That's a good question. So if, you're saying why can't we just do this? Because if we want to use that idea, remember what happens if we have 5 minus 4 over 5 minus 3, hypothetically? I don't think it's negative 4/3. Because if I look at that, I know it's negative 1/2, or positive 5 minus 4 would be negative 1, or 1 over 2 would be 1/2, right? We can't factor out just these first pieces. If you wanted to try to simplify it, and great question, Liam. If we wanted to try to simplify this, we would be, and I'm going to go one step further, what would come out of this numerator part if I wanted to factor something out of just the top? So Kennedy, we made eye contact there for a second. What could I possibly take out of that circled piece? So just the circle, what do both of these have? Yeah, if I tried to factor it and simplify, I'd be left with a and a b minus 1. And if the bottom, if I factored out a b, I'd be left with an a minus 1. And here I can tell very clearly there's no common factor that would divide out. Cool. I wish I could control z on this, but I can't. But I might. There we go. I'm good with this answer. This is the one that I would have. Sweet. Okay. Do we need to work all of them? Okay. Of B, C, and D, which other one would you like to work? We'll check the answer on the other one. Ms. Moyer, which one do you want us to look at? B or C or D? D is the ugliest. Now, C is a close second. Bravo, my hope is everybody was able to do it because you rearrange it, you do a little bit of factoring, and it works out. But let's look at this guy. How many of you guys struggled with delta here? Fair. I think there's probably more than 2 of you realistically, but that's all right. At risk of speaking for all of your classmates, where do you think people struggled on delta? What made delta the hard problem? The fractions. You know what's better than fractions? No, that's not true. That's bless you twice. No, first of all. Maybe. I don't know. It's subjective. Maybe decimals are better. Can we all agree that not fractions are better than fractions, though? Okay, so there's a couple ways we can go through this. When I look at these, I am always going to try to do the most efficient thing. Can you guys tell me, like this one's dividing by 3 on the outside, and this one's dividing by 4. Is there a number that both of those go into? What do 3 and 4 both go into? 12. Now, I'm going to do this in one step. If I wanted to multiply everything by 3, it would bust this fraction. And if I wanted to multiply everything by 4, it would break that fraction there. I'm just going to do both of them at once. If I multiply both sides by the same thing, it's okay. It's allowed. So here we go. Let's just see what happens. I'm going to use a bracket because it's going to look a little nicer. If I multiply this side by 12, and I know it seems random right now, but I promise there's a reason I'm using 12, and 12. Let's just see what happens. I'm going to give you guys like 30 seconds. I want you to distribute just to this 2/3 and just to this 1/4. Since they're all tied together, I'm only going to do it to that front piece. 30 seconds. I want to see what you get. Distribute 12 to both sides. get most things finished. Did you do the 12 or did you do it twice? And then you treated it? Okay, fair enough. I'll ask you in a second because you're good to do that. I think this is easier, but we'll see. The left side's harder, right? I think. When we're looking at this, if I have 12 times 2/3 times this mess, I'm just going to do the 12 times 2/3. That's the easier part. What does that become when I distribute? Because there's only one big thing that we're multiplying to, even though there's a plus, but it's all stuck inside of parentheses. What's 12 times 2/3? 8. Or 24/3 is what we get, but that simplifies to 8. So on my immediate next line, I think that it's okay to just say, hey, look, we have an 8, and then we still have our 3/5 x plus 9. And it's weird the way it happens, but it's three things being multiplied. I can choose the first two and do it as I see fit. Over here, 12 times 1/4 is where I'm going to distribute. What would we come up with? 12 times 1/4 becomes 12/4, I think. What's 12/4? Okay. In this first step, it may, in my mind, it looks a lot nicer. Do you guys agree or disagree? Okay. Once we get here, we still have a little bit of fraction stuff to deal with. What would you do, Fred? We made eye contact there. Yeah, let's distribute. What's 8 times 3/5? 24/5. So we'll just distribute here. I'm good with that. 24/5 x still, plus what's 9 times 8? 72 equals, and this one I'm just going to distribute myself, 3x times, or 3 times 2x is 6x, plus 120. Okay, if you wanted to just solve it here, you absolutely can. But bless you, if you don't like fractions, what do I multiply both sides by to get rid of that ugly fifth? Let's multiply both sides by 5. And I'm going to use my cheater notation where I just draw brackets around the entire thing and do my 5 here. So let's just distribute it to everything. Michaela, if I do 5 times 24/5, can you tell me what happens? If I distribute this 5 to the 24/5 x, does it feel okay or does it feel kind of... So what do I get when I multiply these ones? 24/5 times 5. So we're going to pause here. You're not doing anything wrong. How many of you guys, I hope you're all thinking about it, even though I called on somebody already. How many of you are already trying to do 5 times 24? Okay, don't. I'm multiplying by 5. What am I dividing by? Let's just say they're gone. If I multiply and divide by 5, they divide out, and what's the only thing left here? Good. 24x plus, and this is a bigger number, I think this is 360, equals, because I'm just distributing to everything here, both sides. What's 5 times 6x? 30x plus 600. At this point, I now have an expression in front of me that has no fractions anywhere. This is not the only way to do the problem, but it's the way that I view it, especially if I don't want to think about fractions. I'm going to subtract 24x to each side, and I'm going to subtract 600 from both sides. And I know it's weird to have x on the right, but I want to keep it positive if I can. If I subtract 24x from each side of this, what am I left with? How many x on the right side of this equation? 6 of them. And I'm going to subtract 600 from each side of this equation as well, and I get negative 240. We are one step away. Sonny, to solve for x, one more step. Yeah. Divide by 6, divide by 6, and we should wind up with x is negative 40. Cool. Looking at these, some of you in here distributed right off the bat and you dealt with the fractions the whole time. A-okay. Completely fine with it. If you want to avoid the fractions, this is our route. All right. As a quick check, I don't see my other... Oh, yeah, I do. Let's see if it works. Questions there? Issues, concerns, compliments? All right. So let's see if I can... they updated to Windows 12 or whatever number this is, and I don't like it because it feels like a Mac. Got it. Get out of here. No. All right. So checking things out, just to verify, on Charlie, I multiplied by 5 right off the bat to break the fractions, and we get -2 for x. On Bravo, we rearrange, we distribute, everything works out, we get x equals -4. Now, it happened to show up twice, so -4 and -4, but I'm cool if you just wrote it once. All right. First page, honest feedback. Thumbs up says everything felt really good. Everything felt okay, especially after we spoke, or everything feels awful and I hate it. You don't have to broadcast it to everybody, but okay, fair. All right, on the back side, you guys love piecewise functions, right? How many tables do you have on number 3? 2. Now, looking at these, is this one, should we do this one together? Okay, so Liam said 2 tables. I think I'm okay with that. Why are there 2 tables? There's 2 pieces to this function, right? So I'm just going to make a top and a bottom table. We'll call this the top piece. And let's look. For the top, are there any x values that I have to pick? -1. How'd you come up with that? It's the boundary. This is it right here. Now, the other big part, because these are piecewise functions and we have like boundaries and rules that we're following, there's another mark I'm going to put right here. Is it? So I saw Sunny. I just couldn't read your lips there. Closed or open? Why? The or equal to part. So notice the one thing I'm doing a little bit different, just in the interest of time, is I did not include the middle column. If I plug in -1 for this, what's -2 times -1? 2 plus 1. So there's a point. Give me any other value that I can use for this top table. -2. That's a reasonable choice. If I plug in a -2, I get -2 times -2, which gives me +4 plus 1. 5. Boom. Is that enough for the top table? Yeah, it's just a line. I can deal with that. Awesome. So let's switch gears here. For the bottom table, and we'll use green color for this one, I need 2 values because I can tell it's a nice linear function again. Give me a value of x, Mark, that we might use on that bottom table. 3 would work. I'm okay with that one. If I plug in a 3, 3 minus 2 is 1. Now notice, I don't like that one. Notice that I wrote that one a little gap there. And Mark, you didn't give me anything wrong with it, just so you're aware. But is there another value that I have to have? So 1 won't work because remember we have to be greater than 2, but my boundary is at 2. Open or closed? Open. And when we plug it in, what's 2 minus 2? 0. At this point, we have all the information that we need. There's only one last little place where I'm kind of expecting people to make mistakes. And it's a reasonable mistake. I saw a few people make it. I can't draw straight lines, so you all just have to bear with me. Here's my lovely graph, and I see I'm going from -1 to 3 in the x's. And I'm just going to really roughly eyeball these. Hopefully that's okay. I didn't need any negative, but that's all right. Okay, my first function, it goes from -1 and everything to the left, right? So let's go ahead and switch to the right color here. What's the first? I guess I'm just going to plot it. -1, 3. Would you guys believe it if I said it's here? And then -2, 5 up here. Okay, there's one mistake that I saw a couple different people make on this, and it's really easy to make. When I start drawing this, where should I put my pen first? At -1, 3. And then which way am I going to draw? Just through the next point. Remember, this part of the function is only defined or only works if x is less than or equal to 1. The most common mistake people make is having this line come all the way through, but that function doesn't exist for that part. So we can't use that bottom part of it. For the second one, I'm going to plot both points, and let's just see. I get the point 2, 0. So there's 1 and 2. There's 2, 0. And then 3, 1 would be about right here. Where should I put my pencil to start? So not at 3, 1. Whoever said that, remember we want to start at the boundary. I'm going to start here, and which way do I go? I'm okay with up through the other point. There's a million ways to word it. Here is the appropriate graph for this one. Did I make a mistake? What's up? Ah, look at that. Cool. Thank you for the catch. That was not intentional, just for the record. Okay, the domain and range part. If you have the graph, my hope is not terrible, but I understand that some people still struggle with it. What's domain asking for? The x values, and I can't draw the straight lines like I normally do here. That's okay. If I have a straight vertical line, does my function touch when x is -3 somewhere? Or -4, or -5? Like, it's going to keep touching, right? No matter how far left we go. When does it stop touching? At -3? At -1. Do I actually get to touch the x value at -1? Yeah, so I start at -infinity and I work to -1. Okay, so we'll write that first part. So we'll just say the domain. And I'm going to write it as interval notation. X is in the interval, starting at -infinity and going to -1. How do I show that I touch -1? We bracket. All right. Now, I have to skip a few values in here. How do we indicate that? We union it. So here we go, union, with just this U without the tail. And where does my graph pick back up? What x value will I start using again? At 2. And how far to the right will it keep going? To infinity. Do I get to touch 2? Nope. Open circle as Naomi corrected. And look at that. We have it. Okay, domain stuff. And we'll get to see that again on the next question also. Just a heads up, we are going to start the lesson today. We're going to ease into it. I'm not going to give you homework over the weekend. And then starting Monday, we'll kick back into full speed. Cool. What about the range of this? What's the range even asking for? The y values. What's the smallest y value that I almost touch? 0. Is there any value above 0 that I never touch? Literally every single one. So if we're looking at the range of this thing, we can say it's the set of all y in the interval. If we want to do it in this way, we start at 0 and how high up? Infinity. And look at that. We done. Cool. All right. Do we need a really quick brain break? Okay, so here's the deal. I'm going to give you guys, I wish I could make this smaller than 2 minutes or 5 minutes, but I can't. You guys get 2 minutes. I want you to talk with your neighbors. I want you to identify the coolest thing that any of you did over the break. And then I want you to share that with each other. And then I'll call on each small group and say, what's the coolest thing that happened for the person in your group? Everybody understand that? Somebody say no. Cool. Talk it out. What's the coolest thing you did over break? Starting now. If you guys didn't know, I don't remember if I talked to you about it. Starting next week, assuming they get in, I have a student teacher coming in. So starting next week, we will have Miss Jessica Sweet. Miss Sweet, I don't really know a whole lot about her other than she has a bachelor's in math and a minor in astronomy, I think. But I'm going to leave it. I've never met her in person. I've been emailing with her a little bit, but she will be here with us throughout the second semester. Cool. Kennedy. Interesting. Like the full on conversation, you left your mic on. Yeah, I was watching the video and I was trying to watch it. It's like you didn't pause it either, so it was just a entire conversation. Probably not. I can't imagine there's anything inappropriate, right? No, okay, thank goodness. Fair. All right. Astronomy is a study of space. It's like astrology, but real. No, zodiac signs are astrology. Nope. Astrology is a pseudoscience. It's not a real science. Astronomy is the study of space and planets and exoplanets and those things. Cool. All right. So today we're going to get a very brief start at our new chapter. And in chapter 4, we will be covering everybody's favorite idea. I'm going to write a symbol here. I would hold off a second. I just wrote a fancy Q. What does this mean? Rational, which is, give me another word for rational. If something's a ratio, what does it mean? A fraction. So We are going to be looking in chapter 4 at a bigger class of functions. We've dealt with lines, we've dealt with quadratic stuff, which is parabolas. We even dealt with some of the curvy ones with all of our fancy factoring. Chapter 4, we are going to be talking about rational, and if you would rather write that than the symbol, I'm okay with that. Rational functions, which means all of a sudden we're going to start getting some functions that happen to have variables in the denominator. If you look at that readiness thing that we did, there was one problem where we had x's in the denominator. That's what we're going to be facing this chapter. So to start us off, we're going to start in 4.1, and we're going to be talking about inverse variation. Now, this is a very fitting thing for science stuff, and most of you guys are in biology right now, I think, or roughly half of you guys are in bio. This shows up a whole lot, this idea of inverse variation, all over the place in physics, all over the place in chemistry. A lot of different modeling stuff that we do has this inverse variation that shows up. And we're going to dig into what that really looks like. So for today, our first section, and I should have done it here, we're actually just going to define inverse variation. So sorry to be redundant. Inverse variation. Now, when we think about things that everybody has seen from physical science, do you remember the idea of momentum? Or at least the word momentum. What has more momentum, me throwing a marble at 2 miles an hour or me walking at 2 miles an hour? Why? I have more mass, right? So do you guys agree that if I was looking at just momentum, and if you don't recall, it's okay, it's the mass of an object times its velocity. If I increase the mass, does the momentum go up? If I increase velocity, does the momentum go up? Yeah, so those two things, they vary directly, is what we would say. As one goes up, the other one goes up. Or if one goes down, the other one goes down. When we start looking at inverse variation, it just switches between one of these. So we'll just say that by definition, inverse variation is simply going to be a relation. It's a relation between two variables. So it could be x and y, it could be two physical ideas, but I'm okay with x and y. A relation between two variables where one increases as the other decreases. So one of them goes up, one of them goes downward. Now, we will see a pretty cool example of this. Musical instruments, stringed instruments specifically, the way that tone and everything comes out is an inverse variation relationship, and we'll do a problem like that tomorrow. But there's a really easy way to write these models. For these, if we're looking, and I'm just going to do a little asterisk to say, look, we're still talking inverse variation. The model that we use for this is going to have the form y equals k over x, where this value of k right here, depending on the problem, this will change, but it's just simply a constant, and it gets a special name. It's called our constant of variation. So that's it. As x gets bigger, y gets smaller, or as x gets smaller, y gets bigger. Those are the two things. Every single model will have this form. Now, if we wanted to rearrange this and we didn't want fractions, what do I have to multiply both sides by to break those fractions? By x. And I'm just going to note here, we'll just say note, that if I did that, I would get xy equals, and that's by multiplying both sides by x. What would be left on the right side of this? Or what would remain on the right side of this equation if I multiplied both by x? It's k. Notice, whatever these numbers are, x and y, they always multiply to be k. Hence, it's my constant of variation. It doesn't change. Now, there's a lot of situations where we see these. For example, k could be 30. It could be 5 and 6, right? Or it could be 10 and 3. And we can see there's a whole bunch of different possibilities that would work for this. We're going to deal with it primarily in this form, but it's nice to see that this is where that constant idea comes from. So, Michael, you're looking at me like, what are you talking about? We'll see it here in a second. Okay. 1 goes up, 1 goes down, y equals k over x. That's it. So as we're dealing with these, we're going to jump right in with an example and see if we can't just play around with it. So we'll make a comment here right off the bat. We're going to use inverse variation. And I'm just going to say use it. And I assume it's implied that it's inverse variation, hence because it's what we're talking about. And let's look at one. On our first and probably only problem today, we're told the following. Two variables, x and y, are inversely related. So right off the bat, inversely related tells me we're talking inverse variation, which means I know that the model is going to be this lovely y equals k over x. So let's keep setting this problem up and see what we're actually trying to do. For this, as long as we know that they are inversely related, here's our actual problem. I want us to find y when x equals 6 if we're told that y is equal to 3 when x is 10 or equals 10. So we've been given some ordered pair and we're told that they vary inversely and we get this setup. Now, as we look at it, right off the bat, I know the model that we're going to use. The fact that it's inversely related tells me that I can just use this y equals k over x. So while you might not have to write it every single time, especially as we're getting kind of practice with it, that's where I would suggest we start. Let's just use our model, and you don't have to physically write it every time, but this first time it's nice. We know that we get to use y equals k over x. One last little time, how did I know it was k over x? What here told me that it was going to be this model? What keyword out of this? One more time. Find y. But there's other types of models, and I know we haven't talked about a lot of them, but something specifically told me I get to use y equals k over x. One word here, Sunny. Inversely. This is my inverse variation. If you see varies inversely, this is the model that we use. Now, if I want to be able to find the value of y given something specific, the only thing that I need out of this is a value for k. So let's just see. Is there any information that we can plug in for x and y and solve for k? When y is 3 and x is 10, right? So let's just plug those in. I know that we're given this information. I'm going to plug a 3 in for y and a 10 in for x. Can we use this to get that lovely constant of variation, that k value? What's k in this problem? 30, and it's easy to solve for it. I could do the x times y part, or if I just plug in the information that we're given, we can say, hey, we'll multiply both sides by 10, and we'll just notice that, hey, this implies that k must be equal to 30. Once I have that k is 30, we have everything that we need to find our other value. So we're now given, and I'm just going to say, I'll write way more than we'll normally do. Now, our model, instead of k over x, what did we just find k was? 30. So instead of k over x, I now know it's 30 over x. This is the model that we're working with. And now we can finally finish this last little part of our problem. Before I continue on, have I lost anybody throughout this? Now I'm trying to find y when x is what? 6. Is there a place that I can plug in a 6 for x in this new equation? Pretty standard. That's a weird way to word it, but hey, so I'm going to switch to a lighter blue so it's easier to see. Sorry about that. I think that we can just say y is equal to 30 over 6. And what do we get for y? 5. So check it out. If I said, what is y when x is 6, what do we just find? Boom. When x is 6, and I'm going to write this as a quick, easy sentence. When x equals 6, y equals 5. Okay, at the start of class tomorrow, we are going to jump right in with a problem about some stringed instruments. Cool. Peace out. Check, check, check. Cool.